Let's refer back to the equations for the potential energy stored in a capacitor. This can be calculated in one of three ways. 1/2 times the magnitude of charge stored on the plates times the potential difference across the plates, or 1/2 times the capacitance times the potential difference squared, or lastly, the magnitude of charge squared divided by 2 times the capacitance. 1/2 QV, 1/2 CV squared, or Q squared over 2C. Simple enough, but this leads to perhaps a bit of a contradiction. We can ask the question like this: what if we take a parallel plate capacitor, get it charged up, so the top plate is positive, the bottom is negative, and then we pull the plates farther apart. So instead of a plate separation of D, we have a larger plate separation. Now we know what that's going to do. That's going to decrease the capacitance, right? Less capacitance as the plate separation goes up. The question then is, what does that do to the energy stored on the capacitor? Well, this equation, this equation suggests that if C goes down, the energy also goes down. But this equation says if the value of C decreases, then the energy goes up. Well, it can't be both. Right, this does seem to lead to a contradiction. Well, the problem is we haven't really determined which quantity remains constant in that process. As the value of D goes up, we know the value of C goes down, but we don't know anything about the value of Q or the value of V. And those are the other quantities we have to take into account when considering these equations for energy. So here's the thought experiment. Let's put more detail into what we're doing precisely with the capacitor. So to charge the capacitor up, it had to be connected to some source of potential difference, like a battery. Let's say we have a switch that we can use when charging the capacitor. So we're going to close the switch, allow charge to build up, and then we're going to open the switch back up. Well, if that's the case, by reopening the switch, once charge has already been built up, now there's no pathway for that charge to travel and redistribute or recombine, right? The value of Q is now going to be fixed or held constant. So now when we separate the plates, there's some electric field that's stored in the space between the plates. And as we lift it up and we make the value of D greater, so maybe we have a way to stretch these wires or something, so the plate separation becomes much bigger. That electric field stays the same in magnitude. You can use Gauss's law to convince yourself of this, as long as we don't increase the plate separation too much. In other words, as long as D, or what we might call here D prime, is much, much less than, well, this is really two-dimensional plates, right? We can picture it like square plates and squares with a side of A. So as long as D or D prime is much, much less than A, then the spacing doesn't have any effect on the strength of the electric field. But if that electric field stays the same strength, and this value of D has gone up, then the voltage, which is equal to E times D, has gone up, right? So here's what we're saying. D has gone up. We've chosen to move the plates farther apart. So we know without a doubt that means capacitance goes down. because the switch is in the open position, that means Q is a constant. And lastly, the voltage has gone up. So if we want to consider what happens to the amount of energy stored, we think of these equations 1/2 QV, Q squared over 2C, or 1/2 CV squared. Probably the best equation to think of is this equation, right? Because we know Q is constant, so it doesn't factor into anything. So if the value of C has gone down, then the amount of energy has gone up. Well, likewise, I guess we could have looked at this first expression. Q is constant, V has gone up, so, like we said, the potential energy has gone up. If we try to look at this last equation to answer the question, we can't be too sure. We know the capacitance has gone down and the voltage has gone up. So we really can't be too certain what's happening to energy, although the voltage is squared. And so the quantity that's going up has a greater impact in the equation than the quantity that's gone down. So I guess, yet again, we would probably agree that in a case like this, the potential energy has gone up. So the idea is if we charge a capacitor and then we open the switch up and we lift the plates apart, the potential energy has gone up. Well, that makes perfect sense to me. Remember, the top plate is positive, the bottom is negative, and so they have an attraction to one another, right? So if we physically took our hands and tried to pull these two plates apart, we're pulling against an attractive force. We would have to do work to make that happen, and the work that's done becomes the increase in the potential energy. Let's continue this thought experiment. This time, we're going to imagine the same capacitor with an original plate separation of D. We close our switch, and then once again we pull the plates apart and make the value of D increase. Okay, without a doubt, that's going to make the capacitance go down. The electric field is going to stay the same, and so is it really though? I'm not so sure this time. So you think about it. If the switch is still closed, as we move these plates farther apart, the one thing that has to stay the same, maybe we put the symbol for ground here, so we know the electric potential at this point in the circuit has to be 0 volt. I don't know, this could be a 6 volt battery, for example. So the electric potential here is 6 volt. So the electric potential here has to be 6 volt, and here has to be 0 volt. And even if we move the plates farther apart to a separation of D prime, as long as the switch is still closed, this is going to be a path that leads us to a potential of 6 volt, and this is still going to lead us to 0 volt. And so actually, no, the voltage this time is the thing that stays the same, right? Well, the only way the voltage can stay the same is if the electric field gets weaker, because after all, the distance has gone up and voltage is equal to the product of electric field and distance. So if the distance has gone up and the voltage has stayed the same, the electric field has gone down. Now, how in the world can the electric field go down? Only if the amount of charge goes down. So if this is maybe Q naught, then the value of Q has got to be less than Q naught. How could that be the case? Because as we move these apart, with the switch closed, there's still a full path for electrons to travel. So if this is our negative plate and our positive plate, some of the electrons, as we lift these plates farther apart, are moved through the circuit and back onto the top plate. And so we neutralize a little bit of the charge. And so the value of Q has gone down. And so the question is, what's happened to the amount of potential energy stored? Well, let's let the equations be our guide. 1/2 QV, 1/2 CV squared, or Q squared over 2C. So let's look at the first equation. Q has gone down and V has stayed the same, so we would think that the potential energy has gone down in this case. What about the second equation? Okay, well, the capacitance has gone down and the voltage has stayed the same, so again, it seems like the amount of potential energy has decreased. Let's look at the last equation. The charge has decreased, the capacitance is in the denominator and it has decreased. So maybe we can't be too sure, except for the fact that charge is squared, so the fact that the numerator is decreasing more than the denominator is decreasing, again leads us to believe that the potential energy has gone down. Pretty neat, huh? So we have to make sure that in any case, whether it's a conceptual question or even a numerical problem that we're solving, we should always relate it back to some sort of diagram. In some cases, our diagram might be a circuit diagram, but always take the time to fully conceptualize the problem. Otherwise, physics just becomes math for the sake of math.